Welcome to this lecture for the course Data Structures and Algorithm that is offered to the students of Department of Computer and Software Engineering. And this course is specifically meant for batch of 2022 of Computer Engineering bachelor's program. And I'm your instructor, Dr. Tyler Mehboob. Today's topic that we are going to study is time and space complexity, as we are done with all the algorithms and data structures that we have studied in this course. So I'll summarize the complexities of this algorithm in terms of time and space. So the algorithm that you have studied and the data structures for storing your data, most commonly you can use arrays, linked lists. And the issues that we are concerned is how much space is needed to store our data within your hard disk as well as into your runtime environment, into your RAM. And we need to be concerned about the time required to complete these operations on the data stored in these arrays. And some of the operations that we are familiar with is retrieval, insertion, deletion of the nodes or the contents within these data structures. And how frequently do we use these operations? That's the main concern that will affect the time required to run that algorithm. So we have studied the course of data structures and we have come across several structures to store our data. For example, initially we started off with the array and then proceeded towards the linked list type data structure. And then we studied the queue structure and the stack structure, and we moved to trees, then heaps. So all of these data structures we have studied. Then graphs. We have studied these data structures and we have learned the operations that can be performed on these structures and what is the time efficiency or the time complexity of these algorithms as we proceeded studying these structures. So we are aware that the data that we need to input or store within these data structures and to retrieve and perform operations on these data can be of different types. That could be string type data, it could be integer type data, it could be float type data. So we have different data types, character type data. We could be storing any kind of these data types or values, and your data can be put into different structures where there is no structure present, just a collection of values. Or you could have a linear structure where the order matters, where the sequence matters. Then we have a key value pair setting of your data, and then we have hierarchical structures such as the trees, graphs, such as the trees that we studied, then binary search tree. Then data can be represented in the form of a table or a grid or a matrix, agency matrix. And the structure of a graph, we can use the agency matrix. So then different type of accesses that can be applied. You could remove the data anywhere, you could put the data and retrieve the data, or you could access at the one and only or at the top in case of a stack, and then remove for a certain position such as in a linked list or by value that is stored or by a key. So all these type of different accesses we have studied. And what is an algorithm? So algorithm requires an input of your data. Then there's a sequence of steps or procedures that is applied onto your data, input data, to produce some values as an output. So algorithm is a finite number of computational statements that transform your input into an output. And the purpose of an algorithm is to solve a problem. And we strive to develop an algorithm that gives us the maximum efficiency or maximum performance. So what is a good algorithm? How do we define the efficiency or the performance of an algorithm? Should it be run in less amount of time, least amount of time, or it should consume least amount of memory, or both? In both these cases, we are more interested in the time complexity of the algorithm, because we assume that essentially our hardware has evolved, and so space complexity is not considered as a major bottleneck. So space complexity, we assume, is not a bottleneck for implementation of an algorithm. However, if we design an efficient algorithm, it could certainly impact the performance of our application. So how do we measure the efficiency of an algorithm? The amount of resources consumed in solving a problem that we have designed the algorithm for. For example, you're sorting your data. That is a problem. You have an unstructured data, an unordered data, and you need to sort that data. That is a problem. And we need to solve it using different algorithms. We studied some elementary sorting techniques, such as your insertion sort, bubble sort, selection sort. These were some of the elementary sorting algorithms. And then we move on to better algorithm or efficient sorting algorithms, such as your merge sort, quick sort, heap sort. Then finally we studied the radix sort. So the performance of radix sort is much better than the elementary sorting techniques. So we are interested in time consumption for running these algorithms and how much memory space they occupy on your hard disk for storing, or when you're manipulating the different steps of your algorithm, they are stored in your RAM. So how much space is occupied in that dynamic memory? So it seems that the most obvious way to measure the efficiency is to run it and measure how much processor time it requires. But is it most efficient way of assessing the performance of your algorithm? There are different factors that affect the efficiency of your program, the running efficiency. That depends on your hardware, the operating system, the compiler that you are using, the size of the input, the nature of your input, and the algorithm that you are using. So what is one thing that is clearly in our hands? That is the algorithm and how we structure our data for the input. Essentially, we can measure the efficiency using time and space complexity. So time complexity, we can define the number of times a particular instruction set is executed rather than the total time taken. So rather than the time needed, the exact seconds, milliseconds required to run the algorithm, we are more interested in the number of steps that are required to run that algorithm.